So this problem is grid guardian. So we'll split it into some cases first. So it depends on the parity of the sizes of the grid. So the easiest case to analyze is when n and m are odd. So in that case, we only have one configuration we can do, and that's placing an obstacle at all positions where the row and column index are even. And the reason is, like, if we look at every 2x2 block, like they all intersect at these positions, and there's not really a way to do any less than that. So this is like the only way, like they're fixed at the even positions here, or even row and column indexes. The next case is also not too hard to analyze when n is even and m is odd, and similarly, like if one of them is even and the other one is odd. So if you look at the odd size dimension, we only have to put blocks in the spaces in between, or in the even position. So like basically this and this, like we don't need to put any obstacles in the odd columns at all, because that'll be unnecessary. And for each of these columns, there's 3 ways we can assign the rows. So if you look at the rows, it's even. So we split it into like 2x2 spaces. And initially, like we start with them all at the top part of the even spot, but we can move some prefix of them shifted downwards. So you get a formula that looks like n/2 + 1 to the m/2th power. And this is also flipped if the parities are also switched. So the hard case for this problem is if n and m are both even. Basically for this case, you can split the grid into 2x2 blocks. And then you can initially start with a placement where there's an obstacle in the top left of each grid position, or in each of these subblocks. And we can use a similar idea from the previous case where each prefix of a row can get shifted to the right and each prefix of a column can get shifted down. So for example, like if you look at here, we shifted the first row by 1, we shifted the second row by 1. We didn't shift any of the columns down. This one is like similar to the previous example, except we shifted both columns down all the way. But there can be some corner cases. So one example is like we shift the first row by 1 block, and we shift the second column by 2 blocks. So we kind of leave this middle 2x2 gap here with no obstacles. So we need a way to deal with that. And the way you can deal with that is kind of through some case analysis, or like it's a very local condition that depends only on like adjacent blocks. So to solve this, you can use like a bitmask DP. So let me go to the next page. So use bitmask DP. The DP state is like the mask, which is like which columns you can still shift downwards. And then you have like the current row index and like how much the current row has been shifted. And then to transition, you like iterate through every mask that can go afterwards and every like row shift also. And then you try to see if they're compatible or not. And the way you can do that is like you look at every you just basically want to avoid this case here. So that involves like looking at very local conditions, like at each index you check like that index and the next index and make sure that 2x2 like gap isn't formed. So this leads to an O of 3 to the n/2 times m/2 squared solution, and this is a little bit too slow. So to speed it up, you can notice that if you look at a certain mask and you look at the transitions of the mask that it can reach next, they'll form like a space of, or like each next state will form like a set of submasks from like a fixed mask. So you can speed this up with like a sum of subsets DP optimization, and this will lead to like an O of n/2 times m/2 squared solution, and this is now fast enough. Yeah, that's all.